Hello, in this video we're going to look at a couple more formulae and tree diagrams. So these are the two rules we're going to be looking at, the addition rule and the multiplication rule. They're not like the mutually exclusive rule or the independent events rule, which only apply in certain circumstances. These rules always apply. So the addition rule states that the union of A and B is equal to the probability of A plus the probability of B minus the intersection of A and B. And the multiplication rule states that the intersection of A and B is equal to the probability of A given B multiplied by the probability of B. Let's have a look at the addition rule in slightly more depth. So the union of A and B is equal to the A plus B minus the intersection of A and B. So if we go back to our G and H Venn diagram from the set notation video, the probability of G is 50 over 120, the probability of H is 36 over 120, and the intersection is 15 over 120. Now, if we wanted to work out the union, we could just add 35, 15, and 21, but we could also add the 50 for G and the 36 for H, and take away a 15 because the intersection would have been included twice if we added together G and H, but we only want it once. So that's all the rule is really saying to you, is that the union of G is the same as G and H added together, but you'd have to get rid of any intersection. If this was mutually exclusive events, then the intersection would be 0, and we would simply be saying that the union would be G and H added together. And you can see exactly the same as the sum, 50 over 120 plus 36 over 120 minus 15 over 120 is equal to 71 over 120. And if you're wondering why it's called the addition rule, it does contain a plus right in the middle. So the addition rule was given as at the top, union is equal to A plus B minus intersection. You can swap the intersection and the union around, and it's exactly the same thing, as you'd know. So the intersection would be equal to A plus B minus the union. Also, you can refer to it in terms of numbers rather than probabilities. Okay, so the number that is representative of A union B, which would be 71 in our G and H example, is equal to the number in G plus the number in B minus the intersection of 15 of G and H. So let's also look at the multiplication rule in more depth. It says that the intersection is equal to the A given B times the probability of B. So if you're writing out in that order, then the second letter, the letters that is given, in this case A given B, we're given B, is what the probability that we're multiplying by. So the probability of A given B times by the probability of B. Now from before, again from the set notation video, we know that the probability of G given H is 15 over 36. The 36 represents the whole of H, of which 15 are also in the G circle. Okay, but there's another way of getting there. We could have divided the intersection by the H circle, which is essentially what we're doing with our 15 over 36. But if we're talking about probabilities, the probability of the intersection is 15 over 120. The probability of H is 36 over 120, and of course those 120s are going to cancel out and give us the 15 over 36 anyway. Now it's called the multiplication rule because it does indeed include a multiplication symbol, but I would normally write it as it is in the example. So probability of G given H equals the intersection of G and H over the probability of H, and again it's the second letter in G given H that is the denominator. We are going to finish off with 3 examples just to get the practice of this. So in example 1, we are told the probability of A is 2/3, the probability of B is 1/4, and the probability of A union B is 3/4. And we've been asked to find the intersection of A and B, the union of not A and B, and the probability of A given B. So the first thing I've done is to write the addition rule with the intersection as the subject. So the intersection is A plus B minus the union, that's 2/3 plus 1/4 minus 3/4, which is 1/6. So that's the answer to the first part of the question. The intersection of A and B, the probability is 1/6. What I've then done is to draw a Venn diagram. I've put the 1/6 as the intersection, because I've just worked it out. The probability of A is 2/3. If I take away a sixth from that, I get a half, so that's the rest of the A circle. And similarly, if I take the sixth away from 1/4, I get a 1/12. And that's the rest of the B circle. I can check it adds up to 3/4. Indeed it does. And we also know that the outside of the 2 circles will be 1/4, because we could add up the half, the sixth and the 12th and take it away from 1, or we could use the fact that they told us what the union was, and hence the quarter is the rest. For the second part of the question, the union of not A and B, that is 3 regions. It's the 2 regions that aren't in A, which is the half and the quarter, as well as the region that's also in B, which is the sixth. You could add those all together and get a half. Alternatively, you could work out the intersection of A and not B, which is a half, and take that away from 1. Of course, in this case, you could also get it completely wrong and just work out the intersection of A and not B and write down a half, and possibly no one would be any the wiser, although you are, of course, supposed to show you're working. And then for the final part, the probability of A given B, we start off with the B circle. Now, we already know that's a quarter from the information in the question, but we can also get it from the diagram by adding 1/6 and 1/12. So that's our denominator. Our numerator is the intersection of A and B, which we worked out as a sixth and is still in our diagram. So the probability of A given B is 1/6 divided by 1/4, which is 2/3. Another way of doing it maybe would be to rewrite the intersection as 2/12, and then we can see that the intersection and the rest of B are in the 2:1 ratio, so the intersection is 2/3 of B. Okay, for example 2, we're told the probability of C is 4/7, the intersection of C and D is a half, and we're also told that C and D are independent events, so we can use that rule from before as well. And we've been asked to find the intersection of not C and not D. So I'm going to start using the rule for independent events, which is the probability of C times the probability of D is the intersection of C and D. So that's 4/7 for the probability of C, a half for the intersection. So I can substitute those into the equation, and then the probability of D is going to be a half divided by 4/7, which is 7/8. Then I can use the addition rule, which says that the union equals C plus D minus the intersection. So the probability of C 4/7 plus the probability of D 7/8 minus the intersection a half gives me 53/56 for the union. And if you remember from before, not C intersection not D is the exact opposite of C union D. So I can take away the union, the 53/56 from 1, and that gives me the answer as 3/56. Now, I mentioned in the previous video that there's another rule for independent events, which uses the conditional probability notation, the vertical line, and that would be that the probability of A given B is the same as the probability of A, because if they're independent, then B has no effect on A. Our final example, example 3, has words. The probability of rain overnight is 0.65. If it rains overnight, the probability that the Rounders tournament will go ahead is 0.24. If it does not rain overnight, the probability that the Rounders tournament will go ahead is 0.88. So far, it sounds like a standard tree diagram. Part A, find the probability that the tournament will go ahead. And part B, given that the tournament goes ahead, what is the probability that it will rain overnight? And it's part B that's a bit different because it's sort of backwards in a sense. Okay, we're given that the tournament went ahead, and then what the probability from before of the rain the previous night. So we'll start, as you'd expect, by drawing a tree diagram. We'll start off with rain and not rain. The probability of rain is 0.65, therefore the probability of not rain is 0.35. If it rains overnight, then the Rounders tournament will go ahead with a probability of 0.24. So we've got T for tournament and not T for not tournament as 0.24 and 0.76, following on from our 0.65 of rain. If it does not rain overnight, the probability that the Rounders tournament will go ahead is 0.88. So our 0.35 leads us to a tournament of 0.88 or a not tournament of 0.12. So for part A, there are 2 routes through the diagram which will lead to the tournament going ahead. That's rain followed by tournament or not rain followed by tournament. So 0.65 times 0.24 plus 0.35 times 0.88, giving a final answer of 0.464 for A. Part B, given that the tournament goes ahead, what is the probability there was rain overnight? Now in notation, we're asking for the probability of rain given the tournament. So it's in that order, R line T. And the probability of R given T is the same as the probability of R intersection T divided by the probability of T. Now we've just worked out the probability of T in A, that's the probability the tournament goes ahead, so that's already our denominator. And then for our numerator, we want the intersection of R and T, i.e. rain and tournament, which is our 0.65 times 0.24. So that's our numerator. and then type that into a calculator. As a fraction, the answer is 39 over 116.